Okay, so we've spent some time worrying about measures of central tendency and calculating those, whether they be means or medians or modes. Now what we need to do is we need to ascertain how good of a statistic our mean is. Is it a good predictor of what's going to be seen maybe later on in the sample, or is it a bad predictor because the sample is so variable that it's difficult for us to be able to see if it's a good measure or not? So for every measure of central tendency, there is a measure of something called spread. How spread out is the data? My mean is the average, it's the middle value. My median is the middle value. How spread out is the data around it? Is it really spread out, or is it pretty darn close? Okay, so what I do is I give you a couple of situations here, and I explain why the measure of spread is so important. So here is a data set, 4 values. Here's another data set, 4 values. If I add all these guys up, they add up to 32. If I take the mean, 32 divided by 4 is 8. Okay, so now what we're focusing on is measures of spread related to the mean. Okay, if you look here, this data set, same idea, it adds up to 32, divide by 4 because there's 4 data values and we end up with a mean of 8. So this has got a mean of 8, this has got a mean of 8. Which one is a better predictor of what's going to happen? Okay, is the 8 predictive of what's going to happen next here, or is the 8 predictive of what's going to happen next here? Well, if you look at this data, 1, 10, 1, 10, it's all over the place. Okay, this 8, I have no idea. Is it going to be another 20? Is it going to be a 3? I don't know what it's going to be. So this 8 is not a very good predictor. Okay, not a very good measure of central tendency. Whereas this one, 8, 9, 8, 7, well, it's going to be somewhere around 8. So overall, this is a much stronger mean for this data set than it is for this data set. This mean speaks to this data. This mean doesn't speak as accurately to it. So what we need to do is we need to derive a statistic that's going to allow us to be able to say, this is a good mean because of this number, and this is a bad mean because of this number. Okay? And really, what makes this mean such a good number is that the values aren't too far away from it. Okay, this is only 1 below it, and this is only 1 above it, and the rest of them are exactly on it. Okay, whereas this one is really far off by 12. This one is 7 below. This one is still 2 off, and this one is again 7 below. So largely we're sitting in a situation where this one is so far off all the time compared to this one. Now, this one that's so far off all the time, the distance that it's far off, or the degree that it's far off, or how far off it is, really, is something we call a deviation. It's a simple difference. What I do is I look at my value of my mean, which is 8, and I take my actual x sub I, I subtract my mean, which is x bar, so x sub I minus x bar, and I get these values, -7, or 7 below, that's the 1. This is 2 above, that's the 10, it's 2 above 8. This is 7 below again, that's this one. And then this is 12 above, that's this one. These are all called deviations. Now some of them are negative because they're below, and some of them are positive because they're above. And deviations are great. And if you notice and you add them all up, you're like, wow, that's a lot of deviations. But if I add them all up to get some sort of concerted statistic, I still add up to 0. Okay, that's not useful to me because it's always going to be 0. If my median's in between all these values, it's always going to boil down to 0. Let's try it on the other data set to make sure that's consistent. Okay, so again, the deviation 8 minus 8 is 0. 9 minus 8 is 1. 7 minus 8 is going to be -1, and 8 minus 8 is going to be 0. If I add these all up, oops, I still come to 0. So figuring out the individual deviations and adding them all up is not going to give me a measurement, because this measurement and this measurement is the same for this mean and this mean. But we know this is a good predictor of this data, and this is a bad predictor of this data. So we need something else. So rather than the deviation, one problem that we have is the positives and the negatives. Okay? This is a -1. This is a +1, and 0 and a 0. That's what makes it add up to 0. This is a -7 and a -7, it adds up to -14, and this is a +12 and a +2, which adds up to +14. So of course it's going to add to 0 as well. So one thing you could do is say, let's ignore whether it's above or below. Let's just make it how far off it is. So what we do is we take the deviation and we ignore the sign. The way that we do that mathematically is we take something called an absolute value function. So if I take the deviation and I put an absolute value on it, and that means this one turns into +1. The positive stays positive. This turns into +7. This turns into +7. This is +2, +12. When I add up these, I get to 28. When I add up these, I get to 2. That's a statistic that actually says that they're different. It says this has got small deviations, this has got a lot of deviations. Okay, and as a result, this mean is good because it's not that variable. It doesn't have a lot of deviation from the mean, whereas this one has got huge deviations from the mean, and so it's not very reliable. That's good, that's useful. The only problem is that if I do this statistic, if I had 4 data points here and I had 15 data points here, this actually would have a fairly large deviation just because I have a lot of data points. And all those ones and 2s and 1s would all add up to something as big as this one. So what I have to do is I have to take my absolute value of my deviation and scale it to the size of the data, make it an average deviation per unit point. And that's what this mean deviation statistic is. Okay, it's the absolute value of the deviation divided by the number of data values. And in fact, it's a statistic that's used in some applications, just not as often as we're going to be using it for our purposes this year. Okay, so what we do instead, okay, is we look at a variation on the theme. Okay, instead of using an absolute value function, so we still use a deviation. We take an individual data point, we subtract the mean. Okay, but instead of doing an absolute value to take away the problem of the negatives and the positives adding to 0, what we do is, instead of using an absolute value, we use something called a squaring of a function. Now, squaring an absolute value does almost exactly the same thing. As far as positives and negatives, it does exactly the same thing. So by squaring it, we accomplish the same thing. However, what it does do is it takes values that are let's say values like a deviation of 1, when you square it, it stays 1. You take a deviation of 2 and you square it, it becomes 4. You take a deviation of 10 and you square it, it becomes 100. So it takes big deviations and it amplifies them. Okay, so a deviation of 5 gives you a square deviation of 25, which is huge. Okay, it almost overestimates deviation. Okay, what it also does is at 1, it makes it 1. When you square 1, it's 1. But when you square 0.5, small deviations that are so close to the mean, you square 0.5, it actually drops down to 0.25. So my deviation actually gets smaller. So it amplifies big differences, making them huge, and it takes teeny differences and makes them even smaller. Okay, so that's one thing that the squaring does on top of making positives positives and negatives and negatives. So it's a very useful form of this statistic. Okay, the very first statistic that we use is basically an average deviation, but instead of using the absolute value like we used in the previous page, where we took the sum of all of the absolute value of the deviations over n, and instead we take the sum of the squared deviations and make it over n as well. Okay, now for a population, we use the Greek letter sigma. Okay, lowercase sigma. Okay, and for a sample, we use an S. And S actually stands for the standard deviation, but this variance statistic, this squared statistic, we leave it as sigma squared or S squared. So that's the variance. And all we have to do is we take the deviations, we square each deviation. So first we do the deviation subtraction using BEDMAS inside the brackets. Then we square it, so that's the second thing that we do, and then we add it all up, and that's the third thing that we do, and then finally we divide. Now, one thing that's different between these two between these two formulas, and this is where it actually starts to become different, a population and a sample, is this one's divided by n, a big N, I know. This one's a little n, but this one's divided by n, this one's divided by n minus 1. And the reason why there's a difference between these two is this little n minus 1 allows for something. If you have a very, 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 very small sample size, like let's say this deviation comes out to be 100. Okay? If I have a small sample size, let's say I have 5 individuals, if that's the population, you have everybody, so it doesn't make a difference. So even if it's 100 and you divide by the 5 individuals, it's not that big of a deal. You get a deviation of 20, an average deviation of 20. But if you take this and you divide it by 5 minus 1, you get 100 divided by 4, you get 25. Now why is my deviation or my variance higher in a sample than it would be in my population? Well, if it's a sample and I only have 5 individuals, I could be leaving out a lot of variation that exists in the population. And as a result of that, I overestimate how bad my predictor is. Remember, this is a score that I give to my mean. If I make it too big, I make it less accurate, which it is less accurate if it's a sample because I don't have everybody. But if it's a population, I don't have to worry about making it less accurate. And so as a result, I just divide by this value. So that's what the n-1 does. Read this over here and see if it makes a bit of sense to you. If not, have a look in the book and see if that makes sense to you as well. But if you try these number comparisons here, you'll see that if I have a sample with a sample size of 5 or a population with a sample size of 5, getting a variance of 20 compared to a variance of 25, what it does is it says if I have a sample, I'm less sure about that mean than if I have a population, even if all the numbers are exactly the same. The formula corrects for that and sort of overestimates the variation that's there. Okay, so it's kind of an interesting idea. Either way, in the end, we're going to be using this formula. Now, the formula is pretty complicated. If you look down here, just like we have a raw mean, for a raw mean, we use a raw standard deviation as well. Okay, now standard deviation is just the variance square rooted. That's all it is. So if I take this formula for a population and I put a square root hat over top of it, it's the same thing, same idea. If I take this variance and I square root it, I get the same formula. What you'll notice too is that this s squared for variance becomes s for standard deviation. S, standard deviation, there it goes. This sigma squared becomes sigma. This is the statistic that we're going to use the most. We're also going to calculate variance, but all the variance is one step beforehand. I'll show you when we do the calculations. Okay, so what we're going to do is we're going to go through a sample calculation for a raw score, and then do a sample calculation for a grouped standard deviation. And then they get pretty complicated, but really if you take your time and you go step by step and you use a table, you're going to be very fine at doing these things. Okay, and then you're not going to have any problems. Okay, so standard deviation is a way that we can measure how good our mean is. The smaller the standard deviation, the better our mean. The bigger the standard deviation, the more inaccurate our mean is. Okay, so let's use an example in order to calculate it. Okay, all right, so the examples in your notes that I have are actually yards rushing for football players. Okay, in this particular player is Marshawn Lynch. It's really old data. I just kept the data from year to year and so on. For those of you guys who don't understand, football season is at least 16 games, whether or not the player is injured or not. And so as a result, we have 1, 2, 3, 4, 5, 6, so that we know that we have a sample. This is a sample of the football player's performance. Okay, you don't even have to know anything about this, but the bigger the number, the better they do, whatever. Okay, anyway, so we have all these individual values. These are individual games, and these are the values, the measurements that the football player had. Okay, now to do a standard deviation, the very first thing that you need to do for any standard deviation is you need to calculate the mean. If you go back and look at the formula, you'll see right here, you need a mean. Or right here, you need a mean. If you don't have a mean, you can't do a standard deviation. So your first step is kind of like not really written in the formula. You need to figure out what the mean is. And it's going to be good practice for us anyway. So how do we figure out the mean? Well, it's not rocket science, okay? It's a raw standard deviation, so it's going to be a raw mean. If you remember the formula for a raw mean, it's going to equal the summation of x sub I, all my individual data values, divided by my sample size, n. In this case, if I take all of my yards, all my 6 scores, and I add them all up, I get 618. So I put 618 in the numerator. That's all of my values added up. And then I divide by 1, 2, 3, 4, 5, 6 data values. 618 divided by 6 gives me 103. Nothing too crazy. Okay? Divide 613 divided by 6, I get 103. That means that my mean is 103. I need that to do my standard deviation. Now, again, you have to look at the formula here and treat it like a grocery list of things that I need to do. First thing I need to do is I need to calculate my mean. Second thing I need to do is I need to do this little spot right in here. I need to do the deviation. I got to do inside the brackets and then square it and then do other things. So what do I do in my next column? Well, the first thing I do is my mean. That's what this is, and I get my mean, 103. Beautiful. Then what I do is I say, okay, I'm going to do x minus x bar. That's my deviation, x minus x bar. That's that little part inside in the formula right there. And what do I do with it? Or I calculate that. So I go 110 minus 103, and I get 7. And then I go 76 minus 103. These are my deviations. And I get negative 27. See how 76 minus 103? Okay, it's going to be negative there. Okay. Don't worry about negatives and positives. Keep it as it is. Okay, 150 minus 103 is 47. 103 minus 103, that's an easy one, 0. 54 minus 103 is a big one, negative 49. And 125 minus 103 is going to be 22. Okay, now I haven't finished, so don't worry about the negatives and the positives. Go step by step by step. So first I do my mean. Second, I do inside the brackets, I do my deviation. Then what do? I go outside the brackets here, and I do the squaring. So what do? I take this number 7, and if you notice, it's x minus x bar. Now it's x minus x bar squared. So I square it. 7 squared, 49. Negative 27 squared, you're going to have to trust me, 729. 47 squared, you're going to have to trust me, 2209. 0 squared, that's an easy one, 0. Negative 49 squared, 2401. 22 squared, 484. And then that's a sum. Okay? One thing that's important to note is that this all adds up to 0, but we don't care about that. Because when we square it, the positives become positives, or stay positives, and the negatives become positives. Okay, we add all these guys up. And the reason why we add all these guys up is in the formula, first we did the mean, then we did the deviations, then we squared all the deviations. That's what this square is here. And now what we're going to do is we're going to do all the way the full numerator. And the full numerator, the fourth thing that we do is we add them all up. So we take the 49, the 729, the 2209, the 0, the 2401, 484, and we add them up to 5872. Okay? That's my numerator. That's this whole big mess right here. And it's going to get messier for our other formula. So take your time, pause it, go over it, look at how I've done it here. Okay, I've got my mean. Then that's number 1. Number 2, I've got my deviations. Number 3, I've got my deviations squared. Okay, so that's 2. That's 3. That's 1. Okay, and then finally this is 4, and that goes in the numerator. Now don't forget, we've still got this square rooty thing. Okay, so we've still got the hat of the square root, so square root 5872. That's the hard part. The denominator is very easy. It's just n minus 1. What's my n? 1, 2, 3, 4, 5, 6. 6 minus 1. 6 minus 1 is 5. 5,872 divided by 5 is 1,174. This right here is your variance, which would be, well, we have an x bar, it's a sample, so this would be s squared. But when I square root it, this is my s. Okay, that's my standard deviation. And really what that is a plus or minus thing. Okay, so what this boils down to is I get a standard deviation of 34.3. So my mean is 103. That's my measure of central tendency. So the mean yards per game for Marshawn Lynch is, this particular football player, is 103. Plus or minus 34.3 yards. Okay, which means that, this 103 is a halfway decent measure, but it's really not that accurate of a measurement of how well Marshawn Lynch is going to do in his next game. Or maybe 5 games into the future, who knows? Okay, so we can't really look at this 103 as a terrible amount of accuracy. Okay, and maybe we'll get more and more consistent as the season wears on, or maybe he won't. I don't know. Okay, so that is our measures of spread associated with our mean. Now what we want to do is a grouped standard deviation. And this one looks a little crazier. Remember, with grouped data, whenever we have grouped data, we have 2 things that come in here. First of all, we have m sub I, which is our midpoint. And then we have f sub I, which is our frequency. So don't forget about midpoint. And don't forget about frequency. Okay, so when we look at this formula, we're not going to see x's. Okay, and we're going to have frequencies playing a role in here as well. Okay, because it happens a number of times. Okay, so if you look in the formulas, they look pretty crazy. But you still start with the same thing. You start with a mean. Now, if it's a grouped standard deviation, it's also going to be a grouped mean. Okay, so we're going to have to do a grouped mean. So there's my mean. Then I'm going to do a deviation from the midpoint. Okay, then I'm going to square it. Then I'm going to multiply it by the frequency, because there's if there's 3 3 times this, then there's 3 of them, so you got to multiply it by 3. And then you add them up, and then we're going to do all the rest of the calculations. So it's kind of crazy when you look at it. It's got a lot of features associated with this. Okay? Right, now we're going to go back to way back. Okay, we'll go back to our measures of central tendency when we did our group to work. Okay, but we're also going to go back to even the very first day where we actually did a frequency histogram for this. Okay, these are the marks for our data management class. So this is the entire class. So you could treat it as a sample. You could treat it as a population. In this case, I treat it as if it's a sample. Okay, maybe because it's only one class and maybe I have multiple classes. Okay, so we're going to treat it as a sample. So this is the formula that we're going to use. Okay, now first things first, remember we have to calculate the mean. If you remember the formula for a mean, x bar sub g is going to be fi, oops, I should write down the formula for you. X sub g is equal to the summation of fi mi all over the summation of fi. Okay, so first of all, we've got to go take our midpoint, take our frequency, and go fi times mi. Okay, 44.5 times 1, 54.5 times 4, and so on, and so on, and so on, and so on. In order to get the summation of FIMI, first remember we have to do frequency times midpoint, and then we have to add them all up. And we get this 2324. That gives me my numerator for my mean. My standard my sum of my frequency, that comes from here. I just add up all my frequencies. So it's going to be 2324 divided by 32 gives me 72.65. The same grouped mean that we calculated in our last data set. Okay, but you would have to do this fresh if I asked for a question where you have to do a grouped mean. Okay, and I know it seems like a lot of work because we're just calculating the mean and we've already got an extra column in here. Okay, take your time. Go slowly. It's not going to be that crazy. Okay, so you calculated your mean using the mean formula for grouped data. And you got 72.625. Now what you have to do is you say, okay, I've got my mean, number 1. Number 2, I want to do my deviation. And remember, the deviation is from the midpoint. So what that means is I take this 44.5 and I subtract 72.625. Okay, 44.5 minus 72.625 is going to be negative 28.125. That's my midpoint minus my mean. 54.5 minus 72, I'm just going to put a 72 for simplicity's sake. It's going to be about negative 18. 64.5 minus 72 is going to be negative 8. 74.5 minus 72-ish is going to be about 2. It's a little bit less than 2. Remember, it's 72.625. It's just kind of crazy with how long the number is. But if you follow this all through and use your calculator and take your time, you're going to get all of these deviations. So that's my second step, deviation. My third step is I have to square it. That's what this is. We got to square it. BEDMAS. Remember, we can't multiply before we do exponents. We do our exponents. So we take my deviation and we square it. 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 So 28.125 is 791. 18 squared is about 328. 8 squared is about 66. Again, 0.125, so it's a little bit more. Okay, and we get these values. So this is the third thing that I needed to do. Okay, that's this whole part. Now what I have to do is I have to multiply by my frequency. So that's the fourth thing that you have to do. And I know it seems crazy. It's a lot to do. So what do? I take my frequency 1 and I multiply it by this deviation squared. So 1 times 791.0 gives me 791.0. 4 times 328.5 gives me this 1314. 7 times 66 gives me this 462. 11 times this 3.5 gives me 38.6. 6 times my 141 gives me 846. And 3 times my 478 gives me 1435. So now I've got the whole top, or the whole numerator, sort of. I've got all the individuals calculated. Boom, 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 boom. But now what I need to do is I need to add them all up. Okay, because that's what this summation here is. That's the fifth part to all of this. And I know it seems crazy, but the numerator is the only hard part in all this. So we take all these values, we add them all up, I'm going to get 4887.5. That is my numerator. Okay, pretty crazy. You put in the square root sign, 4887.5 divided by, and then this value here is not 1, 2, 3, 4, 5, 6 groups. It has nothing to do with the number of groups. It has everything to do with the frequency. There's 32 data values. You divide by 32. In this case, 32 minus 1 because it's a sample. So you take 48875 divided by 31, and you get 157.6. This, remember, is your variance. This 157.6 s squared. And then if you want the standard deviation, the sort of deviation brought back down to a normal size again, this is my standard deviation s. Okay, 12.6. So it means the mean test score for the class group data is a 72.6 plus or minus 12.6%. Okay, and that's what that standard deviation tells us. Now that's a handful. There's no question about it. It's not simple. It's not easy. Okay, but for a grouped standard deviation for a group mean, if you can accomplish that task and crunch out those numbers, then you're pretty accomplished. Okay, it's going to take you some time. Okay, but you're pretty accomplished. So make sure you go through that and you crunch those numbers and you work through that assignment where that's indicated, and then you should be fine. Okay, take your time, pause it, rewind, watch it all happen again. Look at the notes. The notes are a little bit more. I've got the steps that we go through, what we calculate first, second, third, fourth, fifth. Okay, all the way through. It's done a little bit neater here. Okay, so have a look at it in your notes as well. The last thing that I want to talk to you about is actually something that we're going to see in this unit, but we're also going to see it all the way near the end of our last, all the way throughout our last unit that we're going to do. And that is something called a z-score. The z-score does involve you being able to do two things. One, being able to calculate a mean, which we learned last lesson. And two, being able to calculate a standard deviation, which of course we just learned like a second ago. Okay, and you need to do both of those. So again, here's your mean, and here's your standard deviation. What a z-score is, it tells you how far away any particular value is from the mean. It doesn't just give you a deviation, because that's what the top here is. That's a deviation. That's a deviation. That's all it is. It gives you the deviation divided by the standard deviation. So it tells you how big your deviation is, and it uses the units of standard deviations away. So it kind of tells you how far is your value in standard deviations away from the mean. And it seems like a little bit weird, okay? But that's what it's designed to do, okay? It communicates the deviation in units that are standard deviations. Okay, so I'll give you an example and I'll explain to you what it means. It's a very easy calculation to do once you have the mean in the standard deviation. Okay, but you need the mean in the standard deviation, which is a lot of work. So you go ahead, you find the mean, you find the standard deviation. Here we've already calculated for previous examples. These are the rushing yards for Marshawn Lynch. Okay, so we've got our mean of 103 yards, standard deviation of 34.3, if you can remember back from our raw standard deviation calculations. So I want to look at a game where he got 76 yards. Okay, that's the individual data value. That's x sub I. X sub I is the individual data value. I want to do a deviation, so I subtract the mean. Okay, so I really go, in this case, 76 is the actual data value. And then I take the mean, 103. Very easy. Okay, 76 minus 103, what is that? 24, 27. Nothing crazy. Okay, now, we see it as a negative 27 because 76 divided by 103 is negative. And what it also means is a negative 27 means that it's negative, it's below the mean. And what I divide by is my standard deviation, 34.3. Now, negative 27 divided by 34.3, it ends up being negative 7.9, or 0.79, which means that the situation for this yard total, this measurement is less than one standard deviation, and see what's negative below the mean, which means it's not too unusual of a situation, not too unusual of a game. He's below what's expected. He's below average, and he's less than one standard deviation below average. So he's not unexpectedly below average. Okay, and we'll talk a bit more about what that means. Let's try another one. This is another game where he got 150 yards, so he did much better. He got more. Okay, in this case, you would take the 150 and you would subtract the mean. Okay, and that's going to be 47. Notice how it's a positive 47, 150 minus 103. The positive means it's above. The negative here means it's below. So in this calculation, the 150 is above. He's above average. How much is he above average? Well, if we take that 47, you could say it's 47 yards, and you're not wrong. But what we want to do is we want to say, well, how unusual is 47 yards above the mean? Is that an expected or unexpected situation? And so what we do is we take the 47 and divide it by the standard deviation, what's sort of expected as a deviation, and we get positive 1.37. What that means is that his performance was above average, and it was about 1.3 times the standard deviation above average, which is a little bit better than one would expect. Okay, because he's more than one jump above it or below. Okay, but in this case, he's more than one jump above it, which means this is a pretty good performance for him, 150 yards, according to his statistics. Okay, right now we're just going to have you be able to measure these and be able to do these calculations. What they mean is an entirely different thing when we put it in the big grand scheme of things, but we got a lot of learning to do before we can do and use these the way we want to be able to use them. So I'm still going to give them to you as calculations for you to do. So these are measures of spread associated with the mean and the mean only.